What's up, pre-calculus students? We're going to do the 4-3 homework where we introduce the logarithm, the inverse to the exponential function that's going to undo what exponential functions do. Now, what does it mean to be an inverse? It's like whatever an exponential function does, which is like grow exponentially large with equally spaced x's, or the other way around. To undo like the growth, what we see is that we are going to have to not grow exponentially large quickly, but grow exponentially slowly. What we find is that you need an exponential more change in your input to produce a little bit of a change in your output. Here, it's like we have this common ratio where it's like every time I move over 1x, we are multiplying, having exponential growth. So we have an exponential change in our y's. Here, to be the inverse, we're going to need an exponential change in our x's to produce one change in like our y's. So it's like I need to, for example, if you're talking about the natural log function, and we talk about the natural log function often, we know that like the natural log of e is 1. To get 2, you need to plug in e squared. To get 3, you need to plug in e cubed. So like the values that you have to plug in your inputs, your x's, have to grow exponentially just to produce a little bit of increase. All that is to say, it's like you can see a equally spaced input, and we can see, and you can find the common ratio by dividing any of these two, that the outputs are growing exponentially, either decaying. They have a common ratio here. So it's 2/3. As x's grow by 1, my y's will be multiplying by 2/3 to get to the next one. This is an exponential function. I could find the equation for it if I wanted to. Here, we can see my y's are just growing by 2. But to get that growth, my x's, you need to multiply by 1.5 or 3 halves. Multiply 3 by 3 halves, you get 9 halves. Multiply 9 halves by 3 halves, you get 27 fourths. So here we can see we are needing an exponentially greater x value to produce an equal change in my y values. This is a logarithmic function. Logarithmic functions typically look like this if it's the inverse to an exponential function. For example, like y equals e to the x has the point 1 e to e squared. The natural log function will have the point e1. It's like the flip-flopped points, e squared 2. Okay, so I kind of explained the difference between exponential and logarithmic functions. Like exponential functions, your outputs grow at a common ratio for an equally spaced input. I say grow / decay. I can say like change at a common ratio for an equal spaced input. This is like tough to kind of like explain, but like it's easier to see. So I'll just show you an example like with a different one. Logarithmic functions, your inputs have to grow at a common ratio to produce an equally spaced output growth. Another example, y equals 2 to the x. You got the point 1, 2, you got the 0.24, you got the 0.38. My x's are going by 1, equally spaced x's, exponentially kind of growing y's, doubling every time. If you look at log base 2 of x, what we will have to see is the flipped flopped points of here. If you looked at plugging in 2, the log base of 2 is 1. We can also put in 0, 1. Okay, that means log base 2 of x has to have the 0.10, has to have the 0.21, has to have the 0.42. To undo, you kind of like map your AB to your BA. So if this goes from 0 to 1, the inverse has to go 1 and take it back to 0. If 1's going to 2, the inverse has to take 2 and go back to 1. 2 goes to 4, 4's got to go back to 2. So it's something I like kind of focus on, and I might talk about it in the class during the loads. But notice we need a common ratio, a growth or a decay, a common change in terms of like a ratio of your x's to produce equally spaced y's. Some things you got to know. It's like, it's probably easier. The best way I like to understand logarithms is to understand its inverse. So like log base 2 is the inverse of 2 to a power. So like 2 to a power, you get like this, like 2 to the x is the inverse of log base 2. So what you have is like situations where, think about 2 to the x, just like I did, have some points on 2 to the x. Log base 2 has to have the inverse points. We'll talk more about how you can like find logarithmic values. It's not really the huge importance of today's class. It's more important for next class. But for an example, if y to the x has the 0.01, I have to have the 0.10 in the log base 2. I have to have the 0.21, 4, 2, 8, 3. See, like the exponential growth for my x's to produce an equal spaced output growth. If I plugged in a fraction, well, like 2 to the 1/2 is the square root of 2. So that means I have the square root of 2 and then 1/2. Let's talk about a negative power. You have the point -1/2 on the graph of 2 to the x. The log function is going to have the point 1/2 -1. You plug in -2, you get a fourth for 2 to the x. That means the log function is going to have the point 1/4 -2. So you end up seeing this graph of a log. You can't plug in 0. You can't plug in negative values because 2 to the x is never negative and 2 to the x is never 0. Log x is the inverse of e to the x. So if I look at e to the x and some points on e to the x, like 0, 1, 1e, 2e squared, log x is going to have the inverse points. Now, the difference is that my log x function, we're going to take the opposite of the y. So I'd still have the 0.10, but I have the point e -1. I'd have the point e squared -2. So I still have the 0.10, but now I have e -1. I have e squared -2. If you plugged in a point like -1, you'd get 1 over e. So that means this function's got 1 over e comma +1. It's like a reflection. This might be different from how your teachers are teaching you this, but it's just like the only way that I can do it that makes sense to me. Let's not worry about the 4 yet. Let's just talk about how log base 3 is the inverse of 3 to the x. I'll have some points on 3 to the x. -1, 1/3, 0, 1, 1, 3, 2, 9. That means the log base 3 function has to map those back. So flip-flop the points. And we get log base 3 of x. Now I'm going to add 4 to all of those. This is maybe not like the exact type of sketch that some teachers are looking for, but you could see if you have log base 3 of x plus 4, you're going to take your y's and you're going to add 4 to them. So it just shifts everything up 4, giving me a third 3, 1, 4, 3, 5, 9, 6. See that we have to have this growth of our inputs to produce an equally spaced growth of our outputs. F is an increasing function, but it's increasing at a decreasing rate. It is increasing slower and slower because you need larger and larger input values to produce a little bit of an output change. So the rate of change of F is decreasing. There you go. F's got a rate of change that's positive because F is increasing and decreasing. F is concave down. Is the rate of change of G positive or negative? G is a decreasing function, so the rate of change must be negative. Rates of change are slopes. Slopes negative means the function is decreasing. Is the rate of change of H increasing or decreasing? So rate of change increasing or decreasing, that's when we talk about concavity. So like the rates of change are decreasing because we are increasing at a lesser amount every single time. So the rates of change are decreasing, or you think about H is concave down. Here, F is concave down, and it's increasing. We can see, though, that flipping it makes it concave up, but that's after a vertical reflection, so let's not worry about it. Yeah, what graph is concave up? G is concave up. All right, kind of like if you skim through that, it's probably fine. This is like the heart of the matter is like why were logs invented? It's to solve equations where we don't know like the solutions because it's not numerical that like a numerical number that we can find that kind of makes sense logically. Like, oh, it's got to be this much in between this and this. No, it doesn't work out like that with this increasing at an increasing rate function. So if you are asked to solve an equation where x is in the exponent, we use a log. How I understand this is like, what do we do to solve for x here? Well, we use the inverse, we square root both sides. The log is the square root to the exponent of x. Pay attention to the base of the exponent. 3e, 4, 100. 10. The log of that base will undo the exponent of the base to the x. I would take the log base 3 of both sides. Okay, now I don't really show it. You can't really see it. I probably would give a little bit more space here, but like it's okay. This is not something like some teachers write, oh yeah, you rewrite it as a log. It's like, I don't like to think about it like that. I like to think about it as it's an inverse function. You just undo. So like we don't use a rewrite method. We don't use arrows. We just take the log like we would square root both sides. The log base 3 of 3 to the x will undo each other and just leave the x. This is our answer. This number, which back in the day students have to look up in a table and use different properties to get like a numerical approximation. This number can be found now using a calculator. So like you could type in the log base 3 of 8 and you get 1.8927. It's just saying 3 to the this number is 8. Now, if I had more decimals, I'd get closer and closer to 8. This number is just like a weird decimal. It's like not a number that is nice. You'd think it's like, well, 3 squared is 9. Maybe it's like 1.9, but it's like, no, it's this 1.8927 number. All right, I digress. I'm like talking too much. It's like getting me ready for the lesson, but let's just like keep going and just do some problems, okay? If I wanted to write the solution to this equation, e to the x equals 10, I would take the log base e of both sides. Make sure you know that the natural log ln is the same as the log base e. Since we see e to the power so often in mathematics, we use a very special notation for log base e. So we don't have to write log base e all the time. We get x equals the natural log of 10. You could plug that into your calculator to get the answer. Back in the day, they had to look it up at a table. Here, I would take the log base 4 of both sides to solve for x. This is something I could find out in a calculator, or you look up in a table, and you get an approximation. Okay? So, other special logarithms. Nah, 100 doesn't have a special logarithm, but 10 does. 10 to the x is used so often in mathematics that we say that if you want to use the log base 10, we're just going to call it log. Without a number associated with it, we're assuming it's a log base 10. So notation you can see is just log both sides for a base 10. You'll get x equals log 2. Again, these are numbers you can find, and you could check like 10 to log 2 will equal 2. I will type in log 2. My Desmos already assumes that it's a base 10. If I change this to a base 10, nothing changes. It's 0.301 either way, okay? 2, 10 to that number will give me 2. See how that works? Thank you, mathematics. Here, take the natural log of both sides. We get our answer. Natural log of e to the x will undo itself, and you get natural log of 1/12 is the answer. Okay? Now, let's say we have more complex equations other than just a number to the x equals a number. Well, we could still use logarithms to solve it. However, if I gave you, 3x squared equals 27, you wouldn't square root right away, right? You divide by 3. If I gave you 3x squared plus 1 equals 27, you wouldn't get rid of the 1. Let's make that 28. You wouldn't get rid of the 1 and then square root. No, you would isolate the x squared. We need to isolate the number to the power in this situation, just like we would normal equations, isolating the x squared before square rooting. Divide by 3 first, then square root. Subtract 1, divide by 3, then square root it. Here, I want to divide by 3 and then use a logarithm to get rid of the 2 to the power and just have the power. I will use a log base 2 to undo the 2 to the power. I get 3x equals log base 2 of 12, which is a number. We can find it, be okay with just leaving it. We will solve for x by dividing by 3. Dividing by 3 is the same as multiplying by 1/3. We are asking you to put your answers in this form. C log base A of B. Here's C log base A of B. That is a number that can be found using a calculator. This is the exact answer. I would not take the natural log until e to the power was isolated. I would get rid of the 5 first. I would divide by 4 second. I do have e to the power isolated. I can now get rid of the e, just leave the power in just like a normal form, not in a power, by taking the natural log of both sides. I get 1/2 x equals natural log 6. Multiply by 2, I get x equals 2 natural log 6. That is in the form that we're asking for. Same thing what I would do first. I wouldn't divide by 4 first, or else you got to divide this 3 by 4 first. I would subtract 3, divide by 4. I get 3 to the 4x plus 1 equals negative a fourth. I don't like this question. It's not possible to do because 3 to a power is always positive. I'm going to go ahead and keep going, but we made a mistake setting up this problem. If I take the log base 3 of both sides, I'll get 4x plus 1 equals the log base 3 of negative a fourth. This immediately sets off bells and whistles. I'm not allowed to take the log of a negative number. An exponential function is always positive, which means you can't plug in negative values into log functions. I'm going to finish it off, but this is not something we can do. There is no solution here. Um, if you attempt to plug in the log base 3 of a negative number, the log of any base of a negative number, it's going to be like, nah, undefined. Okay? So I immediately just put there's no solution. Like this will approach 0 times 4 plus 3, already adding 3 is going to get me bigger than 2. So it's a good one maybe to challenge your thoughts a little bit. I'm going to add 2 first. I'm going to flip both sides. I know this is not something that students are comfortable with doing because you don't see it, but like it's totally easily done is to take the reciprocal of both sides or 1 over both sides. Multiply by 3. This is okay. Take the log base 10. Don't use log base 10. It's the same as just log because we use it so often. We don't have to rewrite it. Log base 10, just log. And this is the answer, log 3 over 20. Cool. Now, conversely, if you have a log, you can undo the log with an exponent. Like where have we seen something similar to that? If you have a square root and you want to solve for x, well, like you would isolate the square root. What undoes the square root? The square. You know, squares undoes square roots undo squares. Logs undo exponents undo logs. Okay, it's the circle. Inverses, undo. So if I want to get rid of the log base 3 and just have x, first I'm going to pay attention to the base, just like I paid attention to the base of the exponent. Whether you see the number or you don't, you should be ready for it. That base to the power of both sides will undo the log. I'm going to use a caret. I like to use the caret so I know that it's like I'm taking it to a power. We use the caret shift 6 on our keyboard to denote that I'm going up or I'm taking the power. So 3 to the log base 3 undoes log base 3, just gives us x. It's not 2 cubed, it's 3 squared. 3 squared is 9. And next class, we'll just be able to know that like the log base 3 of 9 is 2. We'll do enough of them where it's like, oh, it's just the exponent, so we're fine. But for now, we're just going to like do the math, do the undoing, reverse things. 2 to the power undo log base 2. Giving me x equals 2 cubed. 2 cubed is 8. E to the power will undo a base e. E to the first is just e. 10 to the power will undo a log base 10. 10 to the negative second is 1 over 10 squared. That's 1 over 100. Isolate the log before you try to take powers of both sides. There are other properties we are going to learn eventually where it's like, oh, couldn't I just do this? And the answer is yes. But like, let's just isolate the log right now and then get rid of the log. I'm going to do 27 to the 1/3. What is the cubed root of 27? 3. We should be comfortable with that. Subtract the 1, divide by negative 2. I get log base 4 of x is negative 1/2. And it's like, oh, you're not allowed to have a log of a negative. It's like, no. I'm not allowed to plug in a negative into a log. But logs equal negative numbers. We can see like if you plugged in, if this is y equals 2 to the x, 2 to the x has the point negative 1, 1/2, which means log base 2 will have the point 1/2, negative 1. You can get negative outputs for logs. So watch what we get if I take 4 to the power. Ooh, 4 to the negative 1/2. You should be able to do that. 4 to the negative 1/2 is the same as 1 over 4 to the positive 1/2. You get 1/2. Same here. It's okay. Logs can equal negatives, just like you can plug in negatives into exponents. I get log base 2 of x equals negative 3. 2 to the power gives me x equals 2 to the negative third, which is 1 over 2 cubed, which is 1/8. Typically, you plug in a fraction into a log, you'll get a negative number. Because, like, on the other side of things, plug in a negative number into an exponent, you get a fraction if it's an exponential growth. Subtract 1, subtract 1. We don't really have any log bases of fractions, but they do exist, and it's okay. It's like an inverse of a decay. Don't worry about it. Like, we'll see it or we won't. I wonder why. Like, if I'm thinking back to like other log units I've taught, it's like I don't see fractional bases of logarithms, but we do see exponential decays often. Why? Maybe because you can always write, and we learned this last class, an exponential decay as a whole number numerical base to a negative exponent. That's the key. It's like, why don't I see a log base 1/4 when we use 1/4 to the x or 1/2 to the x? Because I could write this as 4 to the negative x, which means we can always use the base of a whole number and then just maybe have an extra step to solve for x by taking the opposite of the answer. This is what we do with math teachers is like sometimes we're like I'm doing this homework video to prepare myself to teach you guys the lesson. Cool. 8 to the negative 2/3 is 1 over 8 to the 2/3. 1 over 8 to the 2/3 we should be comfortable with doing. That's 8 to the 1/3 squared. We use our exponent properties. 2 squared is 4. We get 1/4. Subtract 3, take the opposite of both sides, so that's a negative 4. Take the opposite, I get positive 4. I take e to the power of both sides. E to the power of both sides. X equals e to the 4th. Love doing these problems. They're real-world problems and gives you real-world answers that make real-world sense. Okay, the other ones are just like fun math. These are real-world problems. Like, hey, right now, you could probably get a bank account that earns 4% interest. Literally right now. A couple years ago, you couldn't. But now, like, interest rates are rising. Bank accounts, you get to, we get to make more money with no risk. But you got to worry about inflation. Anyways, we started with $2,000. Okay. How long will it be worth for the account to be worth $3,000? Well, like, let's start with our equation. It's like that would represent the growth of my $2,000. 2,000 times 100%, add 4% per year. Okay? And this is the equation y. Okay? X is time. Y was like the amount of money that you have, your total. Well, we're asking how long will it take for my total to be $3,000? We can solve this. Divide both sides by 2,000. You get 3/2 equals, I'm going to go ahead and simplify this to be 1.04 to the x. How can we solve for x? Take the log base 1.04 of both sides. It will get rid of the 1.04, just leave you with x. Log base 1.04 of 3/2. And I'm going to plug this in because, like, I want to know the answer. If I had $2,000, if you guys, get some birthday money, graduation money, scholarship money, if you put it in a bank account and you want to see, like, how long is it going to take to, grow by a half, grow by 50%, 2,000 to 3,000 is a 50% growth. Log base 1.04 of 1.5 or 3/2. 10 years. That sucks. But that's what you get for non-risky assets. 50% growth is a lot. Think about if this is $2 billion, you'd get a free $1 billion in 10 years. I'll take a free $1 billion. Problem is you have to have the money. Most cars depreciate their value at approximately 20% a year. How long does it take the car that depreciates at that rate to lose half its value? Well, let's pretend my value of my car is $1. Well, I'm going to take 100% of that car, but lose 20% per year. So every year I'll have 80% of my car's value. Okay, well, if my car is worth $1, then how long is it going to take for my car to be worth half of $1? So we got an equation. I don't know why this is jumping around, where I have a half right here. Don't have to worry about the 1. I just have my answer here. Like after I simplify, I got 0.8 to the x. I'll take the log base 0.8 of both sides and get my answer. Now, this is a good one to see too, because this is true. Like cars lose money. You buy an expensive car, congratulations. That car is worth less and less every single day. It's not an investment. It's not something that like is more valuable than just showing off. Unless you get like a really, really like unique antique, cars lose value. It'll only take 3 years for my car to lose half of its value. Let's say you have like a Porsche and it's worth $100,000. 3 years later, it's only worth $50,000. Congratulations. You have your expensive car. A lot of people in this community have expensive cars and they just like, it's just not smart. You know, it's like Teslas. The batteries are going to run out, guys. Like, but enjoy your expensive cars, whoever you have, whoever has them. The enrollment at Lake Travis High School grows at approximately 5% per year. Current enrollment is 3,700. How long will it take for it to be 5,000 students? So we're growing at 5%, so 100%, add a 5% per year, so 105% next year. You know, that's kind of what our thought is. How long is it going to take to be 5,000 students? I'm going to divide by 3,700, and I get 50 over 37. I can't simplify that anymore. I got 1.05 to the x. I'll take the log base 1.05 of both sides. And let's see. This is another real world situation with a real world answer. What is the log base 1.05? How do I get this log base in Desmos? If you're ever doing this at home, log, you type in shift and the dash next to 0, and that's like an underscore. So it's like a shortcut. I think there's a way to potentially have like log base somewhere. Yeah, there you go. Like if you don't know the shortcut, you can click log base. It's funny how they put it in calculus. I guess it's pre-calculus. And then it goes right there. But if you don't want to find that every time, you do shift and then the dash, and it does the underscore. 1.05 of 50 over 37. 6 years. That's crazy. In 6 years, we're going to have 5,000 students in this high school. Good thing we're making another high school. But what we want you guys to do is just have this answer. Okay? All right, that's it. Love this stuff. This is good real world stuff. Don't be intimidated by it. It's just like a square root to a square. Cool. All right, see you guys out there.